Hello everyone. Previously, we discussed using a straight line to explain the relationship between two quantitative variables. In this lecture, we will briefly discuss other curve-fitting models that can be used to explain this relationship. These are the aim of this lecture. When we fit a straight line to the data, we calculate R-squared to measure the goodness of fit of this model. While a high value of R-squared represents a good fit, it is possible that another curve may have a significantly higher R-squared. Therefore, we must always plot the data before fitting a straight line model. These are the commonly fitted curves. We measure the fit of the nonlinear curve using the adjusted R-square. It is easy to obtain equations for different types of curve. It is also tempting to test every mathematical function on our experimental data. However, it is important to remember that we fit the curve to a sample. This curve might not be a true curve. The type of curve that should be fitted is often suggested by the theoretical consideration. It is also important to remember that curve fitting is often not a main objective of our experiments. So we should use curve fitting procedure only as tools to interpret and discuss our experimental data. Let's see an example. In this case, the response variable is yield and the independent variable is nitrogen. Do these data have a linear trend? From the scatter plot, we can see that the data do not follow a linear trend. Let's see what happens if we fit a linear model to this data. The R-square is 70.02%. This R-square is quite high. However, the line is not quite fit. Now let's fit the quadratic model to this data. The R-square is 97.53%. This R-square is higher than R-square from the linear model. This curve fitted the data quite nicely. We can test whether a quadratic curve is significantly better fit than a linear straight line using the F statistics with the degrees of freedom of First, we fit a straight line and find the sum of squares for this model. Second, we fit a quadratic line and find the sum of square for this model and the residual mean square. Then we find the F statistics. The p-value, for 5% significance level, this p-value is less than 0.05. So the quadratic curve is significantly better fit than the linear curve. So far, we discussed about the relationship between one response variable and one explanatory variable. When we have one explanatory variable, a possible reason for lack of fit is that there are other explanatory variables that are responsible for the variation in the response variable. When we have more than one explanatory quantitative variables, we can use multiple regression analysis to describe the relationship between the response variable and all of the explanatory variables. Let's see an example. In this case, we have one response variables and two explanatory variables. Based on this scatter plot, the relationship between student height and their parents' height are linear. So we can fit the simple linear regression for students versus dads and students versus mom. For student versus dads, the R square, this R square is quite low. For students versus moms, the R square, this R square is also low. Now we do multiple regressions. The R square, while the R square is improved, it is still low. So the linear regression for the SMAM height do not explain much of the variability in the student's height. We can do hypothesis testing for each slope, either using a t-test or an f-test from the ANOVA table. We can also do the hypothesis testing for the multiple regression model. Now, can you do this?